Okay. So first of all, I would like to thank the organizers, Ling, James, and Manki, for giving me the opportunity to speak here. I'm going to be presenting my most recent paper with Ginevra Jose and our supervisor, Angel Ranga, on dynamical cobordism and the Swampland Distance Conjectures. So recently we have been dealing with dynamical deadpools. These are tadpoles for dynamical fields. They have nothing to do with Riemann-Roman tadpoles, which lead to topological consistency conditions on your theory. These tadpoles break supersymmetry, and they appear generically in scalar potentials, especially as soon as supersymmetry is broken. As such, they've been used for supersymmetry breaking purposes in some early models that you can see here. And obviously, since you have this new term in the potential, you can't ignore it. And in fact, it's been proven by Alessandro and Angel that this was incompatible with some Swampland conjectures earlier this year. But if you take them properly into account and solve the new equations of motion, then what you end up with is most often a spacetime-dependent solution, a solution that is running. So to quickly go over the motivation for this paper, as I mentioned, dynamical tadpoles are crucial elements to supersymmetry breaking in string theory. They lead to spacetime-dependent solutions I have just mentioned. And the problem is that in general, your solution is going to run into metric singularities or strong coupling regimes, which of course makes their interpretation difficult. So what we wanted to do was to look at a large pool of examples of these dynamical tadpole-induced running solutions, see if we could extract some general features about these solutions, and eventually see how we could link this to Swampland conjectures. So in our last paper with the archive number here, I said it twice, if you have a dynamical tadpole that scales like this parameter t, then we showed that you have a running solution, and essentially you'll run into a singularity at a finite distance, and the distance to this singularity scales inversely to the tadpole as shown here, with n an integer being 1 or 2, depending on if you started with a Minkowski or ADS vacuum before you introduced the tadpole. We also argued in that paper that the physical mechanism cutting off the singularity or space-time at the singularity is the cobordism defect of the original theory, the one with the tadpole. Now I'm going to come back to this in a second, but what we want to do in this paper, what we wanted to do was explore further this relationship between dynamical tadpoles and the Cobordism conjecture. And as you will see, I will also make a link with the mass scale of the Swampland Distance Conjecture and also a bit on the anti-de Sitter distance conjecture. So let me introduce a few small features of the Swampland Cobordism conjecture that I'm going to need for this talk. The Swampland Cobordism conjecture states that if you have a d-dimensional quantum gravity theory compactified on a p-dimensional manifold, then for the resulting theory to be compatible with quantum gravity, you need all of the cobordism classes to vanish. Now, what does this mean? It means that there's no charge, topological or not, in your manifolds that can't be absorbed by something such that you have a finite action process that shrinks this manifold to 0 without running into any problems. From the point of view of the resulting EFT, it means that you have a boundary for any EFT that is consistent with quantum gravity. And in the following, I'm going to be referring to these types of boundaries as walls of nothing. Now, you may wonder, how do we define this cobordism group? Now, the full-fledged cobordism group for quantum gravity is not known, of course, but you can look at specific ingredients of your theory, and then the cobordism conjecture would predict the necessity for defects, cobordism defects that are going to absorb this charge, right? So a very simple example is p-form flex through p-dimensional compact space. Then we know that this is going to lead to a cobordism invariant, which is this charge here that is linked in string theory, we know, to C p-1 form symmetry. So the cobordism conjecture in this scenario is predicting the necessity for d-branes to source and absorb this flux. A completely analogous way of looking at cobordism is to two manifolds being cobordant to each other, which means their disjoint union is the boundary of a p+1 dimensional manifold. But since the Cobordism conjecture states that they should all belong to the trivial class, in a way you can kind of look at it this way. You can kind of glue two of these boundaries together and form from the EFT side, on the EFT side, a sort of domain wall between two different EFTs. And this really speaks to the uniqueness of quantum gravity, right? Which is a motivation for the Cobordism conjecture. And in the following, so I'm going to be referring at these as interpolating domain walls between two theories. So I'm going to give you a spoiler of what we did in the paper, and then I'm going to go through a few examples to convince you. So if you have a theory with a dynamical tadpole in the scalar potential, then as I said, you have a running solution along some non-compact dimension that, well, you have the warp factor that's running, but you usually, well, you always have at least one scalar that is running, and the solution will eventually run into a wall. Now, based on the behavior of the scalar at the wall, on the one hand, we're going to say if the scalar reaches a finite value as it hits the wall, then it's going to be an interpolating domain wall. In the sense, we mean that on the other side of this wall, there's going to be a different theory, which could mean just a jump for the value of this modulus, or it could be a completely different modulus. We don't, this is just an image. On the other hand, if the field reaches infinite values, goes to infinite distance in field space as you hit the wall, we're going to say that it is a proper wall of nothing. There is nothing behind this wall. And given that we are dealing with infinite distances here, we're going to be able to make a nice link with the Swampland Distance Conjecture. So it will go this way. Basically, we're going to be able to compute the distance to the wall on the one hand, and the distance in field space, which is going to be d always, and the space-time distance is always going to be delta, on the other. So we're always going to have this type of link in all of our wall of nothing scenarios. And from this, we're going to be able to link the distance to the wall in space-time to this mass scale of the Swampland Distance Conjecture. That, as a reminder, I'm sure for many of you, it predicts tower of states becoming light at infinite distances in field space as such. So this is going to make us very convinced that these walls of nothing in these dynamical solutions are going to be closely related to the Swampland Distance Conjecture, or at least its mass scale. And I want to stress that we have no microscopic understanding of what happens at the wall. In fact, the whole EFT breaks down. So we don't have a notion of what is the tower states, or if we even expect a tower states in every one of these scenarios. So these are the examples that I'm going to be presenting today, and then I'm going to go through a few final comments. The first is massive type 2a. So in massive type 2a, you have this action here, where you can add this mass term that comes from the zero form flux. And this term sources a tadpole for the dilaton that is controlled by this parameter t here. Now there's a well-known solution to this, which is letting the metric and the dilaton depend on this linear function of a non-compact coordinate x9, because here we're in 10D, right? So you see that there's going to be a metric singularity when z becomes 0, so at b over m, and computing the distance from a random point in x9 to the singularity, you're going to get this, which is exactly the scaling that we predicted in we argued in the last paper. In this case, the underlying vacuum is Minkowski, which is why we have a 2. So as you can see, as z goes to 0, the dilaton is going to blow up, which means we're clearly in a wall of nothing kind of scenario. And in the paper, we argued that this was physically smoothed out, or spacetime was physically cut off by the cobordism defects of type 2a, which is known, and which are O8 planes, right? The Harava-Witten boundary wrapped on the circle of M theory. We can, like I mentioned, link the distance in space-time to the distance in field space, because here we only have the dilaton, so the distance in field space is directly proportional to the dilaton. And with this, we have this relation here between the mass scale of the Swampland Distance Conjecture and the distance to the wall, which, as we get close to the wall, the mass scale of the tower is going lighter. A known generalization of this is just adding a bunch of d8s along x9. And we know in this case that the d8s are sourcing the zero form flux, which means that as you cross these d8s, you're going to have a jump in the mass term, right? So on each side of the d8, you're going to have two different z functions that are both linear, but with a different slope. But the point is that these z functions are going to be reaching a finite value as you hit a d8, which means that the dilaton is reaching a finite value, which means that we're in a very simple realization of interpolating domain walls between two different massive type 2a theories because of the jump in the mass. Okay, my next example is M theory on a Calabi-Yau threefold with some G4 flux. So you have your G4 flux that you can integrate over the various force cycles in your theory and obtain these units of flux or axions here that in the 5D effective action are going to generate a tadpole for the overall volume and the other scalar moduli. We've added some M5s on 2 cycles, which are sourcing this flux. A known solution to this is the following, where we've used the notation of Green, Shulman, Xu from a paper from 2001, which is going to be relevant in the following, where the metric, the volume modulus, and the other scalar moduli all depend on this function A, which in turn can be recast into these one-dimensional harmonic functions here, which are linear functions, where alpha I is related to the charge of these M5s, and the Ci is a constant. Now, these M5 grains are causing some jumps in the value of these AIs, right? They source the flux, and as you cross one, you have different amounts of flux on each side of the M5. And you can you can choose the constants here in the harmonic functions such that they remain continuous as you cross these M5s. And as a result, a very similar example, in a very similar way to the previous example, these M5s are a very simple example of the interpolating domain walls between basically the same theory, but with different amounts of flux, which you could argue are two different theories. But you also have end of the world walls. If you simplify the problem to having only the overall volume modulus, which is generically the case in these walls of nothing scenarios, your whole volume is shrinking to nothing. Your equations simplify and you obtain this. You obtain a singularity at, well, y is a non-compact dimension. You obtain a singularity as y hits 0, which corresponds to the volume blowing up, the volume modulus. So this is fits exactly the description of a wall of nothing. The distance to the singularity and the distance in field space can be linked together again to provide this link between the mass scale of the SDC and the distance to the wall in space-time. A last thing that is interesting to look at, and is the reason why we chose the notation from this paper, is that these authors were observing that in this scenario, the scalar moduli are running along a non-compact dimension. And they were wondering if you could tune things such that they would hit basically the scalar cone wall, and so that you could have a sort of dynamically induced flop transition. So there would be a singularity at finite distance in moduli space. So they did this with 2 Calabi-Yau manifolds with these numbers here, and you can choose the solution so that the flop point happens at y equals 0, far away from any space-time singularity. Okay, this is a different setup. So choosing a more convenient basis for the scalar moduli in terms of these u, t's, and w's, you can show that the scalar cone of the original manifold is this one, while the scalar cone of the flops manifold is this one. And you can see right away that the flop curve is w minus u. Now, in the paper, they proceeded to the matching on both sides of all of these one-dimensional harmonic functions, and it all comes down to the one-dimensional harmonic function corresponding to the flop curve before the flop and after the flop. And as we can see, not only is there a big jump in the values, but a complete sign change. But what is relevant to us is that this is still reaching finite values. And if you remember the flow of equations, you can see that this means that the moduli, volume and other scalar moduli, are going to be reaching finite values as you hit this plot point. So we have, again, an example of an interpolating wall between two theories, but in this case, you really have two different topologies on each side, which is a bit more exciting. But in particular, even if we reached a singularity in field space, there was not a wall of nothing. So this made us even more convinced that these walls of nothing are really something that have to do with infinite distances in moduli space. Okay, my last example are with 4D n equal 1 theories. So if you take your regular 4D n equal 1 theory with the complex modulus, saxion and axion, and so this fancy dressed up version of the saxion, you can compactify this on a circle with some flux on the axion side, okay, on the circle. And this is your the metric ansatz for your compactification. With this, you obtain a three-dimensional theory with a scalar potential, which shows, you've guessed it, a dynamical tadpole for the radion and the saxion. And solving this, you obtain these profiles here. And they are running along a non-compact dimension, which we very cleverly named R, because as you can see, as R goes to 0, the radion is blowing up, which means we reach a metric singularity. And you can verify that this happens at finite distance. So we again have a metric singularity where both the moduli in this case are reaching infinite values. So this is again a wall of nothing. And one more time, we can link the distance in space-time to the distance in field space and subsequently link the mass scale of the Swampland Distance Conjecture to the space-time distance to the wall of nothing. Now, what is interesting in this setup is that it's very similar to that of EFT strings in 4D n equal 1 theories by Lanta, Martusano, Martucci, and Valenzuela earlier this year, where they were looking at BPS strings that have, so this blue thing here, that span time and x, and carry q units of axion charge. So this string is something with a tension that is way beyond the cutoff scale of your EFT, which means that you can neglect all of its oscillations. So this is something purely from the UV. The back reaction of this string on some complex scalar that you have in your theory, it was computed to reach this value, which is exactly what we got for the saxion in our case, by the way. So you can make a direct parallel between our discussion and theirs. And our S1 compactification corresponds to the angle around the string in the transfer space. The direction of our running corresponds to the radial coordinate going away from the string in the transfer space. The axion flux sourcing the dynamical tadpole, which forces the saxion to run in their language, is just the back reaction of the axionic string on the saxion, what they refer to as the RG flow. So our wall of nothing is just their string core. And again, there's a parallel in how you're dealing with the wall of nothing, because we never pretended that we could describe these walls of nothing in the EFT. Like I mentioned, everything breaks down there. And in a similar way, their EFT string is something coming purely from the UV that is not described in the 4D EFT. So in their paper, they were motivated to have a distant axionic string conjecture, saying that basically this applies for any infinite field distance limit for the n equal 1 EFT. So that it can be realized as an RG flow UV endpoints of the EFT string, which means this back reaction on the saxion here. So in our language, this means that every infinite field distance in the 4D n equal 1 EFT consistent with quantum gravity can be realized as a running into a cobordism wall of nothing in some axion flux S1 compactification. But given the examples that I presented today and all the other examples that are in the paper, we were motivated to make this a bit more general, well, way more general, and say that it works for every infinite field distance limits of an EFT consistent with quantum gravity, so for any dimension, and that so it can be realized as the running into a cobordism wall of nothing in a possibly suitable compactification of the original theory. So this is a picture, well, it used to be a spoiler, now it's a recap that I tried to describe for you today. where we have the difference between walls of nothing and interpolating walls in this dynamical representation of the Cobordism conjecture, even if we don't have a microscopic understanding. And I've announced the Cobordism Distance Conjecture on the wall of nothing side.
Matilda, you've got 5 more minutes.
Oh, well, perfect. I'm almost done. The last thing I would like to say is that in a similar way that we linked the distance in space-time to the distance in field space, we can link the scalar curvature at the wall to the distance in field space. And with this, we can obtain a scaling relation that looks like this for every single one of our examples. And in fact, the values are these ones here for the beta term. Now, this is strikingly similar to what you have in the anti-de Sitter distance conjecture, which, as a reminder, states that in a pure ADS vacuum, then the tower of states becomes light as you go to the flat space limit. So even though we're not looking at the same limits at all, since here you're looking at the curvature going to 0, here the curvature is blowing up at the singularities. The setups are completely different, but they both point towards like a lack of decoupling in scales and a breakdown of the EFT. So we thought it was still interesting to point out the similar relation between a mass scale of a tower becoming light and the curvature, the scalar curvature. Okay, so in all of the examples I presented today, I was discussing space-dependent solutions, but it would be of great interest to look at time-dependent solutions. This, of course, for implications with quintessence or inflation, but also to explore to what extent bubbles of nothing are walls of nothing and vice versa. Also looking at patterns in all of these order 1 parameters that we've introduced is and comparing said patterns to what's already been done in the literature would be of interest. And as always, applications to non-supersymmetric strings and supersymmetry breaking string theory remains our main motivation. And although all of the examples I discussed today were very supersymmetric, in the paper we do have examples in a 10D non-supersymmetric string theories in the Sugimoto model, and everything works the same. So we don't need supersymmetry for these scaling relations to work. And with that, I thank you for listening.
All right, let's thank Matilda for the very nice talk. Is there any question? Yeah, Ivana?
Yes, hi Matilda,
Hi.
Thanks for the very nice talk. So I have a bunch of questions really, so I might just ask like maybe 2 quick ones so as not take too much time, and maybe if there's time later. But in the beginning, you showed a relation between the finite space-time distance and the infinite field space distance, right? The delta and the d.
Yes.
So I'm not completely sure I get what it means, because if the d, the field space distance, diverges, ideally, I mean, from all of these examples, the delta goes to a finite non-zero value. So what does it mean to have that asymptotic expression?
So this is a distance from a random point in the direction of your running to the wall. So what we're saying is that as you go to infinite d, so infinite field space distance, you're getting infinitely closer to the wall.
Right, so by delta, you don't mean the extent of space-time in that direction, but you mean...
No, it's a not exact, well, it's similar because in some cases we had 2 singularities along the non-compact dimension, in which case we could really have a finite distance. But in general, we had to take the distance from some random point to the singularity. So we still had a dependence with the coordinate we chose in that sense.
Right. And in general, what do you think this light tower states could be? Because I mean, it's not obvious that, for instance, this corresponds to a decompactification limit or an emergence string limit of some sort. Usually these defects are strongly coupled. Not all of them, but many of them are strongly coupled.
Yes, I can't answer that question. It's a shame, of course, that we lose the complete control of our theory as we go to these limits, and we're using the supergravity in a limit which, well, of course, we're staying macroscopically, far from the singularity, so it's fine, but discussing what exactly happens at the singularity and what tower of states may or may not be becoming light is beyond our framework. I don't personally, I can't tell you what I would expect in these places in every example.
All right. Thanks a lot.
Thank you.
Right, Ling, you have a question?
Yeah. So related to this last question, is there, for some of these examples you've given, perhaps some kind of a holographic dual description? Yeah.
So we've been looking at that in the literature to some holographic duals to boundaries in type 2b supergravity. But yeah, I'm not sure I have anything to say about that just yet. Perhaps we're saving it for future work.
Okay. All right. Thanks.
Okay, if there is no other question, then let's thank Matilda again